Today we are looking at a phenomenon that happens with round things, and the phenomenon is rolling without slipping, affectionately referred to as Rwos. And basically what we have to be aware of is this. We have been seeing a lot of things rotate, but they've been rotating like a pulley on a fixed axis. And so this thing rotates around on an axis that is at rest in a reference frame. And yeah, so what we're going to allow things to do now is to rotate and translate. So it's going to be rotating, and it's also going to be moving, not in that direction as it turns out, moving across through space. And one special case of this is rolling without slipping, which is of course very common phenomenon. It's lots of things roll down hills. Some things even roll up hills, and some things roll on level ground. And they can do so without slipping. So what does it mean to say that it's rolling without slipping? What it means is that if you're a tire rolling without slipping, and you're rolling on sand or snow or something like that where you can see the tread mark, it means that you can see a clear tread mark in the snow after the tire is rolled by instead of skid marks. And what it really means, from the physics geek's point of view, is that at this point in contact, down here with the rolling thing, so this is clearly rolling from right to left, where that is in contact with the ground, the relative velocity of the bottom of the wheel and the ground is zero. There is no relative motion. In other words, no sliding at that point. And so therefore it's not slipping. But if it's rolling, then it's rolling without slipping. All right. We're not going to do a ton with it today, but what we are going to do is derive an equation which is going to look amazingly similar to other equations that we have, so it's going to take a little bit of depth of understanding to recognize how it's different. Okay, so so here we go. Before I get into the rolling without slipping equation, I'm going to remind us of two other equations having to do with velocity and angular velocity, and that's what we're going to be developing an equation for with Rwos. For things rotating on a fixed axis, so I say, remember, here is an object rotating on a fixed axis, and looking very much like the one I just drew a second ago. And we have seen two equations that are remarkably similar looking. One is V equals R omega, and the other one is V equals R omega. And the difference between these is that the first one, they both, of course, give you a linear velocity based on a distance and a radius, if you will, and an angular velocity. The first one refers to any point on a rigid rotating object. And it says if you have a point P, this of course is a reminder, we've done all this. If you have a point P, a distance r from the axis of rotation, the magnitude of its speed v is equal to that distance r times the angular velocity of the rigid rotating object. And that can apply to any point, and therefore you might have different values of r depending where the point is. On the other hand, the second equation applies, just misspelled A, applies, applies to a point on the edge is the important thing here, on the edge of the rigid rotating object. And so we have often, when we've written this equation, put V subscript edge to remind us. And the R in this case, of course, is the radius of the rigid rotating object. And so that would, so in this case, the point that you're interested in must be on the edge. This is point X. And R is a constant for this particular rigid rotating object. It's the radius of that thing. And this gives us the linear velocity as big R times omega. Okay. Today we're going to derive an equation that looks remarkably like those. And it basically goes like this. So consider level ground, although what we do, we're not depending on it being on level ground, but this one is. And we have a round thing, which is, let's put it closer to on the surface. We have a round thing, which is rolling without slipping. So in this case, we're going to have it rolling to the right, and it is Rwosing, rolling without slipping. Okay. I'm actually going to use a little relative velocity stuff to derive an equation which might end up being fairly intuitive, but we're going to do this somewhat formally anyway. So the rel stuff, relative velocity, I will remind you, says that, and in this for one dimension, a one-dimensional relative velocity analysis has us saying VAB plus VBC equals V, he says misspelling V, equals VAC. And A, B, and C are three different frames of reference. And I'm going to apply that to this particular situation, wherein I am going to choose three different frames of reference. One is the axis of this wheel, or this round thing, which is rolling without slipping. I'm going to call that A. The second point is on the very edge on the bottom, and that I'm going to call point B at the bottom edge. So that's actually still part of the rigid rotating object. And the third point I'm interested in is the ground, which I'll call point C, or medium C, if I will, or frame reference C. Okay, so I have the axis A, a point on the bottom edge of the round thing B, and the ground C. In a moment, I'm going to use this relative velocity equation, but before I do that, I'm going to say V at the edge of this wheel is equal to omega times R. I know that because we derived this earlier, and it's written right above here. But what I'm now going to do is apply this edge equation, speed of the edge equation, in particular to point B. So now I'm going to write this as V of point B with respect to A, because the velocity at the edge of this rigid rotating object is measured relative to the axis. Keep in mind that these equations up here, the V you get is a V relative to the axis. And so in this case, for point B, that is going to be VBA. And I'm going to write omega times R, and then I'm going to ponder this for a second. What is the direction that B is moving relative to A? So in other words, if you don't think of this thing as rolling down the street, just picture this as a rigid rotating object. Its angular velocity is clockwise. And so the direction of B relative to A, if you're looking down at B, its velocity is to the left. This is VBA. So the next thing I'm going to do is I'm going to define a positive direction. And keep in mind that for my one-dimensional, we're going to have to hear all the announcements. For a one-dimensional analysis of relative velocity, we can designate directions. We're not using vector notation here. We can designate directions with a positive direction, which I'm going to make to the right, and a negative direction, which I'm going to make to the left. So I'm defining the positive direction to be to the right. Okay. If that's the case, then VBA is actually in the negative direction. And so I'm going to say that VBA, in this case, is negative omega times R, where omega and R are both magnitudes. And that puts VBA in the correct direction. It makes it in the negative direction. All right. So now what I want, for reasons you'll see, I want to come up with what VAC is in terms of this stuff. So I want VAC, so I don't have to do anything with this equation. Do I know VAB and VBC? VAB is the velocity of the axis relative to the point B on the bottom of the wheel. So in other words, what we're saying here is, what is the velocity of the center of the wheel relative to the bottom? Well, to write this down, I can simply say that VAB is the negative of VBA, which is from relative velocity. If I'm moving 6 miles an hour south relative to you. You're moving 6 miles an hour north relative to me. The same magnitude, but the directions are reversed. So if I now look at this Rel-Valley equation, I can say, okay, VAB, well, that's negative VBA, but VBA is itself negative omega times R. So VAB is omega times R, positive omega times R. That's nice. What is VBC? VBC is the velocity of the bottom of the wheel relative to the ground. Well, this object is rolling without slipping. It's not sliding, it's not slipping. And so that means that VBC is equal to 0. It isn't moving relative to the ground. That's the whole definition of rolling without slipping. So what that tells us then is that if I go back to my original Rel-Valley equation, and I'm going to move it down here, VAB plus VBC equals VAC. Okay, VAB is omega R. VBC is 0 equals VAC. So VAC is equal to omega times R. What is VAC? Why do we do this, by the way? Well, what VAC is the velocity of A, which is the center of mass, this, assuming this to be a symmetrical round rotating thing, which it always will be. This is the velocity, VAC is the velocity of the center of mass of this round thing relative to the ground. And what we're seeing here is that this value, VAC, is magnitude omega R to the right in our reference frame. So what we've come up with then is an equation that says this is the product, and this probably seems more complicated than it had to be, for an object which is rolling without slipping, the velocity of the center of mass of that thing is equal to omega times R. This looks like the third version of the same formula. If you go back to, if you go back up to here, we wrote the formula once for point P on a rigid rotating object. Then we looked at the formula again. That's for a point on the edge. This looks like the same formula. They are subtly different, or maybe not that subtly. These two both, the two that we're looking at right here, both refer to points on a rigid rotating object. And for those, we're getting the velocity of a point on that round thing relative to the center. So this second one is the velocity of point X relative to the center. The first one, V equals R omega, is the velocity of point P relative to the center. The formula we just came up with is actually somewhat different, even though we end up, it looks very similar. But this one says, okay, I've got a round thing rolling without slipping down the road. And this equation says, take a look at how rapidly it's rotating. It's angular velocity, how many radians per second it's rotating. Multiply that by the radius of the wheel, and that gives you not the speed of some point on the wheel relative to the center. It gives you how fast is this wheel moving down the road. So if the wheel is attached to a bicycle or attached to a car, it gives you the speed of the car, or the speed of the bicycle. And that is equal to the rate at which the wheel is turning times its radius. All right. We'll do a couple of other things. One thing we'll do with this equation is we will differentiate it with respect to time, because we can. And for that, we get dv dt, which is acceleration, this is linear acceleration, is equal to d omega r dt. Well, the r is a constant. This is a round thing of constant radius. And so this becomes r times d omega dt, which is equal to alpha times r. So the acceleration, linear acceleration of the center mass is equal to alpha times r. All right. These things are all going to become useful. The last thing I'm going to do is say a little something about kinetic energy in the context of all this. Suppose you have an object which is Rwosing, rolling without slipping. How much kinetic energy does it have? And in this case, what we will do is say that it has both. The most convenient way to analyze the kinetic energy of this thing within the reference frame of the road that it's moving down, is to say it has rotational kinetic energy about its center of mass, plus the whole thing is moving down the road. It has translational kinetic energy because all of this mass is translating down the road at the speed of the center mass. And so the total kinetic energy you will find in this wheel is equal to 1/2 I omega squared. That's the energy, kinetic energy it has due to its rotation, plus 1/2 times the mass of the wheel times the velocity of the center mass squared. That's also going to be something, a relationship that will be useful as we analyze things that are rolling without slipping. So I'm going to call that good, and I'm going to do probably 1 or 2 practice problems in a separate video.